All right, so in this case, again, we want to use a known power series in order to find the power series expansion for a new power series. And the two tools that we're investigating to do that are differentiating power series and integrating power series. So let's see how that happens to apply. So again, the idea is that we are given a power series, and that power series has an interval of convergence of radius r, and it's centered at a. Well, if the function that it represents, f of x, is a differentiable function on that interval from a minus r to a plus r, then taking the derivative term by term of our power series gives us a power series representation for the derivative of the function, and that power series remains valid on our interval. So on the exact same interval, our center and radius don't change when we take those derivatives. So we can differentiate power series term by term to get power series representations of derivatives. And by that same token, if our function is continuous and we've got the integral of that thing, then we can, again, take the integral term by term of our power series, so we can use the power rule to obtain a power series representation of the integral of our original function f of x. So we obtain a new function from there, and again, our interval of convergence stays the same in that our center and radius are exactly as they were for the original function. And so that's the technique that we're going to use in this particular case. So here we have our function f of x equal to, so we don't need the f necessarily, we have our function 1 over 1 minus x quantity squared equal to the series n equal 1 up to infinity of n times x to the n minus 1. Okay? And we know that this thing is going to be valid in between negative 1 and 1. And so if we take the derivative of both sides, so 1 over 1 minus x squared, and then we can take the derivative of our power series, again, term by term, nx to the n minus 1. It doesn't change our interval of convergence, so over here on the left, we have a negative 2 times a 1 minus x to the third power, and then times the derivative of the inside would make that a plus 2. So for our power series over on the right-hand side, now we've got a series n equal 1 up to infinity of n times n minus 1 x to the n minus 2 power. And so what happens really for our first term, we could, if we plug in n equal to 1, this would give us 0 in our first term, so we can imagine this thing starting at our series n equal to 2 up to infinity, because our first term is going to be 0 of just n times n minus 1 raised to the n minus 2 power. Okay, so this gives us a power series for 2 over 1 minus x to the third power, and that gives us our series n equal to 2 up to infinity of n times n minus 1 times x to the n minus 2 power. Well, now we do a trick that's kind of common, because what we wanted to do was to use this to evaluate a series n equal to 1 up to infinity n times n plus 1 times 1/2 to the n minus 1 power. So this is what we wanted to evaluate. So somehow can we transform this into a series that looks like something involving 1/2? Well, we can do that, and we can do that by doing a change of index. So if I pick a new variable, say m, equal to n minus 1. So what happens in that case? Well, my m is equal to n minus 1, so m plus 1 is equal to n. And so I do something kind of similar to my u substitutions back in integration. Here I have n starting at 2. Well, if n is 2, 2 minus 1, m will start at 2 minus 1, or 1. As n goes off to infinity, so does m, so my upper limit is still infinity. My value for n becomes m plus 1, and my value for n minus 1, well, that was m. And so what happens to my power on x? N becomes m plus 1 minus 2. And so in the end, I get a power series that starts off at m going from 1 up to infinity, m times m plus 1, and x to the m minus 1 power. And so now if I do a substitution and let x equal to 1/2, then what I obtain is 2 over 1 minus 1/2 to the third power is equal to my series m going from 1 up to infinity, m times m plus 1, and 1/2 to the m minus 1 power. And so what happens evaluating my function, this becomes a half in the denominator, so I have a 1/8 in the denominator when I raise it to the third power. And so what does this really become? 8 times 2, I get a value of 16 over that. And so here I've actually used my power series, and what enables me to do that is that my power series expansion was originally between -1 and 1. Well, 1/2 is within this interval. So I do have -1 greater than 1/2 less than 1. So since this was a true value, that's what really enabled me to make this substitution and to then figure out what this series will actually sum to. So I hope this has been insightful, and I will see you guys in the next example.